In this segment, we will take up a problem from axial loading, and the problem statement goes like this. There is an annular hollow cylindrical tube basically. So it's aluminum tube, and then inside this there is a brass solid cylinder placed, and on one side they are fitted like this with an end cover, okay, and the other side there is this brass cylinder is slightly longer than the aluminum tube. Now when we try to plug this in the other end cap through this screw thread on the aluminum tube, um, there will be a gap. This small gap will remain, but then what is done is, if we turn this end cap um, by a little amount, so this gap can be completely closed. This gap will be closed by two processes. One is this aluminum tube will be slightly elongated, and at the same time this inside brass cylinder will be compressed, and both of them will contribute towards closing of this gap. And it's given that the pitch of that thread is 1.5 millimeter. That means if we turn a complete one cycle, then it will move axially by 1.5 millimeter. Now it's given in the problem that the gap gets closed once we turn 1/4 of a complete turn. Okay, so that means 1/4 of a pitch is the total movement that happens in axial direction. Now if that is so, and then all the other parameters like geometric parameters like outer diameter of the aluminum tube, inner diameter of the aluminum tube, and the diameter of the solid brass cylinder, everything is given. E for aluminum and E for brass are also given. Now, so how the main thing here is to um, uh, think about what's happening at the interface basically when they are joined. See, if you draw the um, free body diagram of the aluminum tube, okay, so if I draw it like this, and then what will happen is it will be under tension, so a pull force will be acting like this. Suppose this is P, then on the inner cylinder, that is the brass cylinder, okay, the same amount of compressive force will be acting because there are no other external loads. Okay. So that's how the forces will be balanced, and because of this force there will be extension, say delta in the aluminum will be, say, PL over E of aluminum and A of aluminum. Now this A of aluminum is nothing but pi over 4 d outer aluminum squared minus d inner aluminum squared. Okay, so this is how the area will be calculated, and EAL is given. Then P, so this will be a function of P, and the length is given to be 0.25 meters. Okay. And then at the same time, the delta of the brass tube will be equal to negative of the same PL over E brass to A brass, and A brass will be equal to pi over 4 d brass square. Okay, so this is how you should calculate, but then the main important thing comes. Now see, this is an extension and this is a compression. Now the gap which is initially there, which is actually getting filled up by these two movements, um, can be, suppose the movement because of the rotation, I'll say is a delta star is 1/4 of the 1.5 millimeter, so that will be your 0.375 millimeter. Okay, but then uh, the idea is that the summation of these two basically, or you can say the absolute value, the summation of the absolute value of these two is uh, uh, equal to this. That means if I draw here, what will happen is this will be elongated by certain distance like this. I'm exaggerating the picture here. This will be elongated. Similarly, this will be compressed. This will be compressed a bit, and then um, whatever is coming from this side and whatever is going from this side, both this, so this is in a way delta aluminum, and this is delta brass. So its magnitude and its magnitude, if you add them, that should be equal to this one. Okay, okay, so if I write now that thing, so P L over E A L A A L plus, I'll take the magnitude of this, so P A L P L over E brass to A brass, this is equal to delta star. Now from here you can calculate the value of P, and it will come out to be 27.308 kilonewton. Now if this is the force of action and reaction, then now we can calculate the stress which is actually desired, that the stress which exists in the aluminum tube and the rod. So the stress in the aluminum tube is equal to P over the area of aluminum, and this will come out to be 67.9 megapascal, and then sigma of the brass tube will be compressive, so P over area of the brass tube, and it will come out to be minus 55.6 megapascal. And similarly, if we want to calculate the extensions, so will be the delta of aluminum will be um, calculated exactly from the same these equations, so you don't require to, I'll not write it again, you can just check with the answer. So this will be 0.2425 millimeter, and delta of the brass rod will come out to be minus 0.1325. This minus sign is for telling us that it's a compressive force, compressive means compression. Yeah, so this millimeter. Okay, so this is how you should calculate. Here I want to make one more point, that see, suppose you were given that along with this there is a temperature difference, and because of which there is an extension or compression due to thermal or thermal coefficient of different materials. So you just have to do one thing, that in place of calculation of this deltas, here one more term will be coming, and that will be that L times alpha, say aluminum times delta T, and here it will come to be, so plus again one more term. That's the only thing which will change, and rest all will remain same. And again you can calculate everything under that condition, whether the temperature is decreased or increased with respect to the temperature at the assembly time. Okay, so that's a problem about axial loading. You should be very clear about this, and we will meet with another problem of axial loading in the next segment.